Okay, now the method of ordinary least squares. Fine. So, well, this method is attributed to Gauss. He is a German mathematician. Now, under certain set of assumption, the method of least squares has certain statistical properties. Now, first of all, remember this that a two-variable population regression function is given by yi equals to beta 1 plus beta 2 xi. Well, we also know this that population regression function is not directly observable, so we have to resort to sample regression function, which is given by yi equals to beta 1 hat plus beta 2 hat xi plus ui hat. Okay, well, this could even mean yi hat plus ui hat. Okay, yi hat is the estimated value of yi. Okay, yi hat is the estimated value of yi. Okay, I'll just write it somewhere. Yi hat is the estimated value of yi. Fine. So how is sample regression function estimated? Well, from this equation, we had the equation this yi is equal to yi hat plus ui hat. This gives us ui hat is equal to yi minus yi hat. Clear? But yi hat is equal to beta 1 hat plus beta 2 hat xi. That is beta 1 hat plus beta 2 hat xi, which is equal to yi minus beta 1 hat minus beta 2 hat xi. That is your ui hat. Clear? Well, what are ui hat? Ui hat are your residuals. Okay, ui hat are residuals. Okay, that is they are just the difference between the actual y values and the estimated y values. So I'll give you an example, the example of the education. Okay, on in one column you have an actual value of yi, that is actual level of education which is being attained. On the other column you have the estimated value of yi. See, there is some regression equation you would have estimated. You have the value for all the independent variables. You have the value, the coefficients from the regression equation. You will multiply them, okay, and you will get the estimated value of yi hat. I'll be giving you examples as I go. So you would like to determine the sample regression function, which is as close as it is possible to the population regression function, that is your yi. Okay, so you will choose sample regression function in such a way that supposedly, if this is one of the criteria, that the sum of the errors is equal to 0. Sum of these residuals is equal to 0. That is summation of yi minus yi hat is 0, or it is as small as possible. Okay, well, there is actually some problem. There's actually some problem with these kind of these kinds of criteria. Okay, I'll tell you the reason being. Supposedly, if you adopt this criteria, okay, well, if you adopt this criteria and you have this as a sample regression function, okay, that is, this is your sample regression function, this is x and this is y. Clear? Well, and these are your different UIs. Fine. So this is U1, U2, U3, U4, and this is your these are your different UIs, that is your U1 hat, U2 hat, U3 hat, U4 hat, and so on and so forth. So the first and the last residuals, they are very far from sample regression function. Okay, and while this second and third, they are very near, and but all of them, they are getting equal weight. Okay, even though they are very near or far. Okay, they're very near or far, they're getting the equal weight. Fine, that is, they're getting equal weight. They are so, but this is a problem because they should be actually getting different weights. Fine, so that you can have certain criteria. With this, it is also possible that the sum of these residuals, okay, might even come out to be 0, okay, but still they're getting equal weight. So that is a problem. So you would rather adopt a least square criteria. So you would be adopting what is called the least square criteria. That is, instead of just adding these residual, least squares, squaring, least squares criteria. Instead of just adding them together, you would be actually squaring them and adding those squares. Okay, so what exactly you would be doing? You would be doing this, that you would be adding the squares here. That is this. So summation of ui hat square is equal to summation of yi minus yi hat square. Clear? Which is actually equal to summation of yi minus beta 1 hat minus beta 2 hat xi square. Clear? So by under this rule, okay, the sum can be small, okay, even though these residuals, they are widely spread out than the SRF. Okay, that is in this criteria. But under the least squares criteria, okay, larger is this value, larger is this estimated value, larger is the square. Least is the estimated value, least is the square. Okay, so this is the reason you actually go in for the least square criteria, and not for the simple criteria as just this, that just minimizes sum of these residuals. Okay, so this is one answer, that why actually would you adopt the least square criteria. This is a very simple answer to it. There might be some other reasons also. For that, I would urge you to actually have a look at some good books like Gujarati, Johnston, Donado, Kementa, etc. So kindly have a look at them. Thanks.